Hi everyone. I'm a PhD student in computer science, and I'm working with Dr. Shiniwan to for this project. Actually, this is a reinforcement learning-based routing for interconnection network. You can see my content overview here, and like the first question can come to our mind, like, okay, what is interconnection network? If you want to do high performance computing, so you need to use so many computers together, right? So you need to connect all the computers, processors, or memory modules together. So interconnection network is nothing but the network by which you will connect all those things. So now the next question is, okay, what I'm trying to do here in interconnection network. So it's like adaptive routing. What is adaptive routing? Like if you have a source and destination, you can have a multiple minimal or non-minimal path. So, but using the minimal path is not always the wise decision. Why? Just let me give you an example. Suppose this is the source and this is the destination. So there are three flows going from source to destination, and this is the main path. Okay. But so if you just send all the three paths over this main path, these links are shared for three flows actually. That means there will be a flow flow collision or link congestions. But if you do what, if you just take if you send one flow to the main path and two other flows to other non-minimal path, although non-minimal path the latency will be higher, the time will be higher, but in total there will be no flow collision. So that's why in total the system's throughput or system performance will be a lot better. So then another thing, okay, what is reinforcement learning? So it's a branch of machine learning. So here actually our agent interacts with the environment and do some take some actions, and it gets some reward back from the environment, and by this feedback it always improves itself. So actually the goal is to maximize the total cumulative reward, and by having the best policy. So there are many value functions like that. One of the most popular one is the Q value function, or the quality value function. So, and now let's see what are the challenges of adaptive routing. What are the challenges? So if you see there are multiple there are two paths here. This is the source, and suppose there is the destination. So two paths. So a router has only the local information. This is the router. Only it has the local information. What is the local information? That means it only knows, okay, how many packets are waiting to use this path, or to use this link, and how many packets is waiting to use this link. You can see a little number of packets is waiting to use this link, but if you just consider the whole information, global whole path, so many packets are waiting to use this path. So based on these information, if we just take, only one packet is waiting to use this link. So let's try to send the next packet using this link. So it will be a bad idea, because later it will have a less congestions. So that's why we need to estimate this global information for which will be available to each router. So here reinforcement learning can help us to estimate this global information. So why have you chosen reinforcement learning over other machine learning techniques? Again, network states actually changes over the time, because the traffic pattern, or the traffic pattern means different types of application wants to do different things. So, and this changes over the time. So pre-given data set or experience from anybody else is not supervised learning is not a very good idea for this kind of scenario. And again, you need some human effort, but as it keep changing the network state, so it's actually not a good idea. So, and reinforcement learning, obviously it learns by itself, and it has a continuous learning feature. So that's why we have chosen reinforcement learning here. So how can we relate reinforcement learning things into our adaptive routing in interconnection network? We can think of our topology as the environment, all the routers as an individual agent. So it will be a multi-agent reinforcement learning based system, okay, model system. And the states is the different traffic conditions, and the observations and actions is just choosing the next router, or from here, okay, I'll towards the destination, I'll send my packet to the next router. So that's the actions, and the reverse is the traveling time between these two routers. So what are the challenges we have to face, if we want to design a model-based routing system in interconnect? Actually, here we need to have several path diversity. That means obviously as many paths we will have, we can distribute our packets to that over those paths. So it will be great. But we have also the restriction on hop count, because you can't just route your packets without even progressing to the destination. So there is a restriction on the hop count to avoid the live lock and deadlock on your system. And the restriction on link uses. So in interconnection network, there are like several kind of links. Like we can call it like on local links or global links. So global links tends to have like higher latency than the local links. So because it's wide, well, like it's lengthier than the local links actually. So we need to restrict our routing algorithm to use like, we need to use it because like these are actually truly like, you know, distributing your packets over different groups, but like, yeah, there should be some kind of restriction. And then again, sparse update of qtable and qtable updating mechanism, which is like generic to any kind of routing scheme. That means like your qtable update mechanism can adapt to any routing changes also, and the qtable convergence, that's it. So here we are working on routing called Q-adaptive, so which is Q-learning based adaptive routing. So there are actually three principal components, like maintaining a qtable for each router, and like the routing with qtable and updating the qtable. So here you can see this is the qtable. Like each router actually maintains this and learns this qtable. So here we have grouped several routers into a group and like merge them in a single row, so that like we can mitigate the sparsity like of update. So and here actually we do have multiple ports. Multiple ports means like multiple links connected or available to that router. So here we'll store the Q values. Q values is nothing but the estimated latency. That means estimated time. Like suppose here this means like, okay, if you send your packet through this port 1, so it may take this much time to reach to the group 1, like to the destination group. And after getting to the destination group, it's like you can just minimally forward the packet. It doesn't mean, because like in destination group all the routers are connected each other, so there is all-to-all connection there. So and now how the routing with the qtable, how qtable works, like so when a router receives a packet, it knows, okay, what is the mean path port, like what is the mean path, because by looking at the tuples you obviously know that. So it will get the estimated mean path port value, which is we are calling it qmin, from the qtable, and again it will get another best path port. What is best path port? That has the lowest q value. Right now that we are calling it q best. Now we have got two things, qmin and q best. Now we'll compute the difference between them. Like now if that difference there will be a predefined threshold just to bias towards the mean path, because like obviously taking mean path there is a little bit bias, so that's why we are using a threshold value. So if that difference is less than the threshold, then we'll send the packet through the mean path, and if it is greater the threshold, we'll send the packet to the non-mean path. So and again, so this is actually we're saying it, okay, temporary outbound port, but the final outbound port, like we have like to tackle the exploitation trade-off, like we have used a simple but yet I think it's effective like epsilon greedy policy. So to get the final outbound port, that means epsilon, like with epsilon amounts of time you will randomly choose a port, and most of the time you will choose this temporary port, like already exploited port. So now here, how the updating qtable works. Suppose here S is the source and D is the destination. So you want to send the packet from source to destination, and in the path there is a two router X and Y. So router X has already a value, estimated value of QX. So QXYD. That means like, okay, what is the estimated value, estimated time to send a packet from X to router D through router Y, neighboring router Y. So it has already this value. So when router X sends a packet to router Y, and after receiving that packet, router Y does what? Router Y again gets the lowest value, okay, how much time it needs to send to router D, and then it propagates back this value to router X. So you see, like router Y is more close to the destination, so obviously it will be more accurate to this information will be more accurate. So it will propagate back, and using that information, router X will update its own value QX. So it will be, as it is more accurate. So I think it will learn, like it will be also more accurate after a while. So here you can see this is the equation, and like I have. This is the immediate reward. Immediate reward is just like the traveling time from X to router Y, and we have used actually two learning parameters like alpha and beta, because like there's a research work called hysteretic Q learning. They have showed like, okay, if you just always increase your Q values but not decrease, like suppose you are avoiding a penalty, that you can stuck into a suboptimal like a solution. So that's why, like suppose you have taken the best decision, but any other router, like team member, we are calling it team member because like any other router in the path have actually made a bad decision. So for that bad decision, you cannot be actually penalized. So that's why like they have suggested also using the two learning parameters. One is for like increasing your Q values and one is for decreasing your Q values. So by this way, actually we've update the Q value, and the routing works like this. And like, yeah, but I haven't gone through the it is basic level, but because like there are some other restriction obviously also as there are several groups, but like I'm not going through that. And so again, like I'll now come to the conclusion, like due to his learning by own policy, it's obviously a very good choice. And like I have gone through several other reinforcement learning based techniques for different high performance to solve different high performance computing based problems. And they have done a great job actually. They have done some very good improvements. So that's why I thought, okay, why not in applying that thing in like routing also. So yeah, so if anybody is interested, you can also research, like do some good research on it, and you can take it forward. Yeah, thank you. Any question?